Hello, I'm Hugh Manfield and welcome to my science channel. Now today we're going to be talking about some misconceptions about fluid space theory. I've read through some of the comments. Thank you everyone for your comments. But there is a recurring theme that fluid space theory acts like a space vacuum cleaner. And I'm probably responsible for starting that because I've actually said that. Flows in space-time do not move objects around the way a vacuum cleaner does. The misconception is that we're stuck on the Earth because there's a flow of space, kind of like a fly stuck on a piece of filter paper. That's not exactly the way it works. Now, while space-time flows like a fluid, it's not a molecular fluid like air or water. Thinking of space flowing in those terms doesn't really tell you how it actually works. For example, if we took a vacuum cleaner out into space, it wouldn't work because there's no air, and it needs air to work. And even if your vacuum cleaner could pump space-time itself, you still might not be able to move objects around the same way you would with a vacuum cleaner. To get objects to move with the flow of space-time, or what I've called ruach in a previous video, you need some very specific things to happen. Let's take a look at what Newton's laws tell us about space. And I've said this before in earlier videos, that Newton's laws of motion should actually be called Newton's laws of space because they tell us the properties that space-time has. For example, an object, according to Newton's first law, set into motion will remain in motion forever. So what does this tell us about space? It tells us that objects move through space without resistance. And there have been studies done by different physics institutes trying to put a number or a limit on that amount of resistance. And basically they've come up with very, very small numbers. Essentially, space is frictionless. Masses can move through space without resistance. And then you have to turn that around and say then, therefore, space can move through masses without resistance. And that's an interesting logical step, and it's not a step a lot of people like to take. Einstein didn't like that step, and it conflicts with the ancient philosophers and the Renaissance philosophers who handed down this space denial in their philosophy. Now, back when Einstein was growing up and being educated, the concept of matter was totally different from what we have today. Matter was considered to be some sort of volume, presumably of even density, that occupied space. And matter was different from space. There were two separate things. In fact, the Renaissance philosophers like Kant argued that space shouldn't even be considered, only objects. And you'll see this in Einstein's writings, that he considers the relationships of objects, and he tries not to talk about space itself. Eventually, even Einstein had to admit that space-time has properties of its own as he developed general relativity. So, space moves through objects without resistance, and it has no mass or momentum. So it's a frictionless, massless substance. So if you were going to blow on an object with the wind of space-time, no matter how hard that wind blows, there's no friction, there's no mass, so there's no momentum transfer, and there's no force generated. So no matter how hard you blow on an object with space-time, it's not going to move. So it's not like wind, or it's not like a vacuum cleaner that creates friction and sucks things in. Moving objects with flowing space is an entirely different process, and the objects move for an entirely different reason from what happens in a vacuum cleaner. So let's go to our old example of Ricky on her ship accelerating through space. So as Ricky's accelerating, she throws a ball to Stan. And from Ricky's point of view, the ball moves in a curve. It falls away in an arc, as does Stan. Stan is falling away because she's on the ship accelerating, and everything in the universe from her perspective is falling away. So Ricky, when she sees the arc of the ball that she just threw, she will assume, Newton's second law is at work. It's following a curve. There must be a force acting on that ball. Well, she's actually wrong. The ball is actually traveling in a straight line at a constant velocity. It's obeying Newton's first law, as is Stan. But Ricky, since she's in an accelerated reference frame, sees the ball constantly changing velocity. But it's not the ball that's changing velocity, it's Ricky who is changing velocity. She's in an accelerated reference frame. So she may imagine this force that she can't explain and somehow acts on every object in the universe. And that's our problem in understanding gravity. We assume that gravity is a force, and it's not really our fault because everyone's taught gravity as a force. If you're a professor out there or a science teacher, you probably teach gravity as a force, and you're doing a disservice to your students because teaching gravity as a force is teaching a useful fiction. There's no force acting on the ball or Stan, but there is an acceleration. From Ricky's point of view, her ship is accelerating through space, so we have to take that and turn it around. Space is accelerating through Ricky and her ship. So if we look at a fluid space analysis of a box or a ship accelerating through space, linear acceleration, what we'll have is a velocity vector field and an acceleration vector field. So fluid space theory is actually a vector field theory. And the velocity is going to be constantly increasing. It's not a constant velocity. Now, Einstein said that you could dismiss background motions of space-time. And if the velocity is constant, you can dismiss that, and you could zero it out. But if the velocity is changing over time, you get an acceleration field, and you can't dismiss that because you'll feel it, and you'll know it, and you'll be in what you assume to be a gravitational field. So this is how fluid space theory works. You have a non-constant velocity vector field which generates an acceleration field, and the acceleration field is what causes the effect known as gravity and causes objects to move in curves. And one other thing, the velocity vector field is mathematically related to the acceleration field through a simple term, A equals to v dt. That is, the acceleration is the time derivative in the change of velocity. So let's look at another case, and that of a rotating system. In this case, we have Ricky on a rotating wagon wheel space station. And we've cut away the rest of the space station. We're just showing a small room where Ricky happens to be. So what we'll have is, once again, a variable velocity vector field. And it will be running around the circle as Ricky swings around the circle. And it will be very small near the center, and the velocity will increase as you move away from the center. So you have a non-constant velocity vector field, which generates an acceleration vector field that is acting downward relative to Ricky, and she feels the gravity as she swings around in the wagon wheel space station. And in this case, the acceleration vectors and the velocity vectors are 90 degrees from each other. And that allows this to go on essentially forever I mean, once you set a wagon wheel space station into motion, it's going to pretty much rotate forever according to Newton's first law, and you'll have onboard gravity at no cost going on and on forever. So this is how fluid space theory analysis would work for a rotating wagon wheel space station. So now we move to the case of mass-based gravity on a planet or sun or moon. So what you're going to have, once again, is a velocity vector field and an acceleration vector field. And the velocity vector field for mass-based gravity is escape velocity. Now, escape velocity is very high when you're down close to the surface or near the center of the mass. And as you move away, that escape velocity decreases and becomes smaller. So what you have, once again, a non-constant velocity vector field, which through the mathematical relationship gives rise to the acceleration vector field. And if you have an object in an acceleration vector field, it's going to accelerate as dictated by that field, and you will experience gravity. So that's how fluid space theory works. It's not like being swept along with the fluid. Objects behave according to Newton's first and second laws, which are actually laws of space. If space is accelerating, an object will accelerate with that space. So the flow of space-time doesn't directly affect an object. It's the acceleration field that causes the sensation of gravity. While there will always be both an acceleration vector field and a velocity vector field, for the effects of gravity, you can ignore the velocity vector field because it's combined like clockwork with the acceleration vector field. If you want to know what's going on with gravity, all you need to do is look at the acceleration vector field. But the velocity vector field actually tells you quite a few other things. Now, another misconception about fluid space theory is that general relativity tells you more about space-time than fluid space theory. And you need general relativity to deal with very massive objects like a black hole, which has a massive lump of matter down at the heart, which causes the projection of this intense gravitational field. Well, the problem I have with general relativity is illustrated by the trampoline analogy. Here we have the sun like a bowling ball on a trampoline. And everyone goes along with that and says, oh yeah, that's really cool. Gravity is like a bowling ball on a trampoline. Well, what's holding the bowling ball down? Gravity. So you're using gravity to illustrate gravity. And the thing about general relativity is a trampoline is a static thing. It has no dynamic component to it. Once it's deflected, that's it. It's not moving. And to make it change, you got to move the sun around on the trampoline. So it's actually a very poor analogy. What fluid space theory brings is a lot more than what general relativity brings. First of all, from the acceleration field, you get the Newtonian gravity. And then, if you have the acceleration field, you can work out the distribution of matter within that field based on the accelerations. And you can predict orbits using Newton's law. So, fluid space theory gives you an acceleration field that gives you everything you need to understand gravity within a solar system or a galaxy or any other system. But what general relativity doesn't have and totally denies is the existence of a velocity vector field. And the velocity vector field gives you a lot of information, and it's easy to get. If you have the velocity vector field, which is basically escape velocity from the sun and escape velocity from the earth. And you can combine those velocity vector fields to create an entire field for the whole system. You can get the space-time curvature metric. And how do you get that? Well, you plug the velocity vector into the Lorentz transformation for length, and you get the length contraction at any point in the system. And it's very easy, and you don't have to do a whole bunch of tensor calculus or fancy math that involves gravitational potential. Plug the velocity vector magnitude into the Lorentz transformation, and you've got the metric. Now, the velocity vector field also gives you the time curvature metric, or the time dilation metric. Once again, you just plug the velocity vector into the Lorentz transformation for time, and then you can know exactly what rate you can expect to see a clock running anywhere within the gravitational system. So it gives you a lot of information that's easily accessible, and you don't have to do a lot of complicated math to get it. Another thing that fluid space theory brings to the table is the drift metric, or the drift velocity metric, which is dark matter. So what's going on in a system is we have this continuous inflow of space-time. So space-time is actually disappearing within the gravitational field of a massive object like the sun or the earth. And this is where the vacuum cleaner analogy was used. I explained that the sun and the earth are like giant space-time vacuum cleaners. They're sucking up space-time. They're gobbling it up, and it's like going down the drain. Not only is it flowing down through the theoretical event horizon, it's being contracted all the way out. And you can create the formula for the amount of space-time contraction that's going on based on the velocity vector field. You take the proper flow of space, and then you calculate the contracted flow of space based on the velocity vector field, and the difference between those two is the amount of space that's being contracted anywhere within your system. And when you plot that curve, starting at the center and moving outward, you get this nice curve that follows the orange curve, which exactly matches the dark matter contribution to the galaxy rotation curve. So the contraction of space-time is another thing that fluid space theory brings to the table that general relativity doesn't. If you're using general relativity, you have no clue that space-time is being contracted within a galaxy. Now, you may have wondered why galaxies look so much like vortexes, like water running down the drain. Well, it's pretty evident that that's actually what's going on. Space-time is being drained away by all the matter concentrated in the galactic core. It's just like a whirlpool of water going down the drain. Space-time is literally going down the drain. But if you use general relativity to study galaxies, you'll have no clue that that's actually going on and that that's what you're looking at, because Einstein had the space denial philosophy. But if you mapped out the velocity vector field for a galaxy and created space-time metric based on the Lorentz transformation, you would get a space topology that would look very much like a vortex of water running down a drain. And this is where the vacuum cleaner analogy actually comes more into play. Within galaxies, gravity becomes very weak, and the frame dragging aspect of fluid space theory becomes more prevalent, and it actually begins to work more like a space vacuum cleaner. Now, if we put a boundary around a volume of space in a galaxy, and we watched over time, that boundary would shrink inward as the space is being contracted away. So space-time is actually vanishing within a galaxy. And that ring would shrink and shrink and shrink until it finally disappeared. And what that means is that space is being taken away, and new space is being drawn in from the universe around it. Okay, so you might ask, well, why doesn't it just suck all the stars down into the black hole if that's what's going on? Well, the stars have adapted to this continual shrinking away, and they're actually following faster orbits. So imagine you're swinging your weight around on a string, and you have it going at a constant rate. And then you reel in some of that string. What happens? The weight speeds up. So what happens to the stars in their orbits? Well, as you contract that space away, they speed up in their orbits, and they reach a point of stability where if you were to take away the amount of contraction, you would see them fly outward in expanding arcs. But that amount of contraction that's going on is exactly enough to turn those outward arcs into circular orbits. And this is what the truth about dark matter is. Dark matter is the effect of contracting space-time within a galaxy. And there's no way any particle detector is ever going to find it because it's not a particle. It's an effect of fluid space theory. It's an effect of gravity itself. So why hasn't fluid space theory caught on? Or when will fluid space theory catch on? Well, we're kind of at a point in physics where everyone's looking around and scratching their heads. There's been very little progress, no new discoveries for 2 or 3 decades. Dark matter detectors keep getting bigger and more expensive that don't detect anything. And there's rumblings about the need for some new theory. But no one in physics is ready to break from the herd and start chasing after some radical new theory like fluid space theory. So don't hold your breath for when that day is going to come. But eventually, I believe there will be a stampede to fluid space theory. But you don't have to wait. You can study fluid space theory now from my website, from my video lecture series, and from my book, Einstein and Aliens, A New Approach to General Relativity, which is available on Amazon.com. So don't wait for the stampede. Go ahead and start learning about fluid space theory now. Until next time, I'm Hugh Manfield.